Swayam Prabha. Digital India. Educated India.
So, last class I have discussed that how we can determine the ultimate lateral load for a pile for freehand or fixed hand or it is in cohesive soil or cohesionless soil. Now, this class I will discuss that about the settlement response of lateral loaded pile, because for lateral loaded piles settlement response is also very important. So, for this settlement response of lateral loaded piles, the first approach that I will discuss is the subgrade modulus approach, because this approach I have already discussed during the topics on concept of beams on elastic foundation. So, I have already discussed this concept for shallow foundation when a beam is placed over springs. So, in that case the springs were vertical springs. Okay. So, and the beams were resting on those vertical springs, but that concept is will be used here for lateral loaded piles, where the springs will be the horizontal springs. Okay. So, first we will assume that this approach will be applicable when the pile is supported by linear spring with constant kh with depth. Now, what is kh? Kh is the coefficient of is the modulus of subgrade reaction, or we can say the horizontal modulus of subgrade reaction. So, this kh is basically the horizontal modulus of subgrade reaction. Or simple I can say is horizontal subgrade modulus. So, in this approach here the piles will be connected with horizontal springs, and the pile will be treated or will be modeled as beam. So, these are the springs, those are connected with the pile, and pile will be modeled as beam. So, this is the spring which modulus of subgrade reaction is kh, and this is the beam which is basically the pile. Okay. So, this is the concept of this approach. So, this approach, the first case will assume that pile as a finite beam, okay? Because as I have already discussed, there will be the short pile, there can be a long pile. So, definitely for the short pile you have to go for the finite beam, but for the long pile we can go for the semi infinite beam. And later on I will give you that when we will go for the semi infinite beam, when a beam is called the long beam or the short beam, because that I have already given during my presentation of shallow foundation, but that also I will give later on, that how the pile will be treated as long pile or the short pile. Based on that we have to consider as a finite beam or semi infinite beam. So, here the first concept, the pile is as a finite beam, and when I discuss about the finite beam solution procedure, then I discuss that suppose if this is your beam which is a finite length for in case of shallow foundation, because this is the beam which is resting on the vertical spring. So, the same thing if I rotate this total system beam with spring, then that will represent as these beams or the piles are with connected with the horizontal spring. So, now if we model this one, and I have already discussed that for different end condition we have to consider some end conditioning forces, say P 0 M 0 or P 0 A M 0 A, so that the boundary conditions can be satisfied. So, first condition in this finite beam problem, we are assuming that both ends are free. So, both ends are free. So, when we apply any load in this particular beam, then we this is a both end finite beam, but we will treat this beam as an infinite beam, and then we will determine the bending moment and the shear force at end A and the B, at end A and the B due to the external load, and then to nullify that bending moment and shear force, or to make the net bending moment and shear force at point A and B 0, we have to apply end conditioning forces. Why we have to make bending moment and shear force 0? Because its both ends are free. So, boundary conditions we see, or the boundary conditions is that moment at A will be 0, moment at B will be 0, and shear force at A will be 0, shear force at B will be 0. So, these four are the boundary condition for this finite beam with both ends are free. Okay? So, that is why initially, as I mentioned, these things have already been discussed in the beams on elastic foundation concept during the shallow foundation part, that we have to consider this beam as a infinite beam. Then for infinite beam we will calculate the bending moment and the shear force at both ends, that means A and B, due to the external load, and then as this boundary condition you have to satisfy for the finite beam, then you have to apply some end conditioning force M 0 P 0 A or M 0 P 0 B, so that the net bending moment and the shear force will be 0 at point A and B, or end A and end B. Okay. So, that is why these end conditioning forces P 0 A and M 0 A we have to apply to make net bending moment and shear force 0. Okay, that is the concept. So, that means this P 0 A, M 0 A, P 0 B, M 0 B are the end conditioning forces are the end conditioning forces to make shear force and bending moment zero at end A and B. Okay. So, this is the concept. So, now for the lateral loaded piles, what are the forces will act? So, we can suppose it is a free headed pile. So, first condition will be the free headed pile, then I will discuss the fixed headed pile. So, before I go for that free headed and fixed headed pile, so how we can determine this kh, because I have already discussed how to determine the kV or the subgrade modulus. So, kh unit is kilonewton meter square per meter. Okay. So, this determination of subgrade modulus reaction or subgrade modulus or the modulus of subgrade reaction or subgrade modulus kh can be full scale lateral loaded pile test. We can do the lateral loaded pile test and we can determine the kh. We can do the plate load test, or we can use the empirical correlations with other soil properties. So, Tazaki, based on the plate load test 1995, proposed the relationship between the KH and the KS1. What is KS1 bar? Is the modulus for a square plate of 0.305 cross 305 meter square size, and D is the diameter of the pile. So, that means these KS1 are the modulus of subgrade reaction. Those are determined by using a square plate of 0.305 meter size, and that is used here to determine the KH for the pile. Okay, so, and here these will get from the plate KS1 will get from the plate load test, and that KS1 values are given for different types of clay soil. So, for steep clay, very steep clay, hard clay, it is given in ton per feet cube. So, this range is given and this is the proposed value. That means, for steep clay, this KS1 proposed value is 75 ton per feet square per feet. So, that 75 ton feet square per feet we will use here, and then we will divide it with 1.5 times of diameter of the pile. D is the diameter of the pile in feet. Okay. So, and then finally, we will get the KH, which will be yes. So, which will be your horizontal subgrade modulus. Okay. So, this is the one relationship which is given here. So, this is based on plate load test, you will get the value. Next one, that Bowles has given some lateral modulus of subgrade reaction ranges for different kind of soil. So, these KH values are given. So, for different kinds of soil, and these are the ranges. So, for dense sand to soft clay. So, medium clay O8, saturated, stiff clay O8, saturated, fine sand, medium dense sand, dense sandy gravel. So, all the ranges are given. And one thing here, that these are empirical equations. So, that is why this unit is again kilonewton per meter square per meter, but KS1 is also the same unit, but as this is are the empirical relationship. So, we can use these relationship, and then the proper unit we have to use as which is suggested, because remember that here D is in feet. Okay. So, and then we will go for few more empirical correlations. So, basic has given one empirical correlations, where EP IP is the pile stiffness, that means EP is the elastic modulus of the pile material, IP is the moment of inertia of the pile cross section, and D is the diameter of the pile. Okay. And ES is the elastic modulus of the soil, mu S is the Poisson ratio of the soil, D is the diameter of the pile, as I mentioned. So, by using these correlation also we can determine what would be the KH value. Skempton has given a correlation based on your CU value, undrained cohesion value of the soil for the clay, and that correlation can be used for the clay. For these are ranges are given. Chain has given some correlation with respect to the pressure meter modulus, because I have already discussed what is pressure meter modulus and then what is pressure meter test in my soil exploration part. So, you can see what is pressure meter modulus. So, that pressure meter modulus can be used to determine the KH of the soil. That means, we can do the pressure meter test, and based on that pressure meter modulus value we can determine the KH by using these two correlations. One is for cohesionless soil, another is for cohesive soil. So, again the KH can be determined by dilatometer modulus also. So, the dilatometer is the ED is the dilatometer modulus, and the FP is the pile shape factor, where this P is in suffix. So, FP is the pile shape factor, which is in between 1.5 to 4 for round pile and 1 for H pile or the square pile. Okay. And D is the diameter of the pile. So, if we know the dilatometer modulus, and then if I apply the shape factor and then the divided by 3.7 into diameter of the pile, then you will get the kh value. Now, for in my previous expression in previous classes also I have discussed that for granular soil we assume that the kh value changes with depth, but for the cohesive soil the distribution of the kh is uniform along the depth. So, but that means here it is mentioned that, as I mentioned, that the stiffer clay uniform kh is observed, but for the sandy soil or the granular soil and very soft clay, the kh is not uniform along the depth. Kh generally increases linearly with depth. So, in such case kh can be represented as in that eta h into z by d. Z is at any depth from the ground surface, d is the diameter of the pile. Okay, and eta h is called as actually it is coefficient of subgrade modulus or unit subgrade modulus. Okay. So, for normally consolidated clay eta h value is given, the range is given, and for sandy soil also eta h ranges are given. So, that eta h ranges for sandy soil and the normally consolidated clay, these values are given, and it is clay means very soft clay, because for soft clay only these variation will be noticed. Otherwise, for the cohesive soil the kh is more or less uniform along the depth of the pile or along the depth of the soil. So, and for the dry sand and the moist sand, submerged sand, all the ranges are given for loose, medium and dense soil. So, that eta h will take from here, then we will put this eta h value here, and d is the diameter of the pile. So, for any depth, if I changes the z value for any depth, I can calculate the kh for the pile. Now, I will go back to that finite beam concept. So, we are talking about that finite beam concept, we have to apply the end conditioning forces. So, now for particular first case, for the free headed pile, so first case free headed pile, suppose this is the pile which is modeled as finite beam. So, it is a finite beam. So, there will be a horizontal load H is acting in the pile. Okay. So, that means because of that H, now if I write it or if I rotate this total orientation of the system, then this is the finite beam and this is these are the springs. Okay, and whose spring constant or modulus of horizontal subgrade reaction is kh. So, here suppose H is acting here. Okay. So, H is acting here, the same thing I am drawing here. So, H is acting here, but now due to the H, as I mentioned, due to this H you have to determine what is the shear force and the bending moment at both the ends. Then you have to apply end conditioning forces, so that net shear force and bending moment will be 0 for free headed pile. So, this is for the free end. So, both ends are free. So, we will apply the end conditioning forces. So, this is P 0, say this is A, this is B, P 0 A then next one is the m0a, then here p0b, this is m0b. Okay. So, these are the all loads which is acting on this finite beam. So, 4 are the end conditioning forces and H is the actual applied load. So, after solving this condition, so I am not giving you the detailed description, I am finally writing the expression of the settlement, shear, force, bending moment and the slope. So, after solving these conditions, so we will get the deflection y. So, this is the deflection at any point within that beam will be 2 h lambda divided by k h d into k rho h. Okay. So, where lambda will be equal to, this is 4th root of k h, because in beam case that was 4th root of k divided by 4 E I. So, that case E will be the kilonewton per meter, k will be the kilonewton per meter square. So, but here I am writing k h which is kilonewton per meter cube. So, we have to multiply with the d, but in the case of shallow foundation that was multiplied with the width of the beam. So, here the diameter of the pile is multiplied. So, k h and then 4 E p I p, where E p is the elastic modulus of the pile, I p is the moment of inertia of the pile section, and k rho h is a value which I will give in tabular form, that for different depth of the pile or depth of the beam, how the k h value will change. So, similarly, the deflection slope, this is for the slope, that is equal to minus 2 h lambda square divided by k h d into k theta h. Okay. So, then bending moment m or bending moment, which is equal to minus h the bending moment equation is minus h by lambda k m h. Similarly, shear force, that will be equal to minus k minus h k q h. So, this is for the moment. Now, the similar expression I can develop for another case if a bending moment is applied. Okay. So, this is the pile with spring So, now if this pile, if this bending moment is applied. So, bending moment is applied. So, if I, because your, yes. So, if the bending moment is applied, then the equation of the pile will be, that means this bending moment is applied. So, for the m0 bending moment, the similar type of expression y will be equal to, this is for the horizontal force, this is for the force h, and these expression are for the moment m0. So, deflection equation will be 2 m0 lambda square divided by k h d, then k rho m, then theta is equal to 4 m0 lambda square divided by k h d into k theta m, because initially it was for the h, that is why h is written, now it is for m 0. So, that is m is written. Now, for the bending moment, this is m 0 k m m, and for the shear force it is minus 2 m 0 lambda k q m. So, these are the equations are given. So, that means for m 0 also similar kind of we have to apply 4 end conditioning forces such that the net shear force and bending moment will be 0. So, based on that we have derived developed 4 equations for the moment m 0 and for the a force h. So, now for the free headed pile, so if it is subjected to h, suppose the pile is subjected to h only, then I will get the deflection of the pile at any point if I use the expression of y deflection. Okay. But for the this is for the free headed pile. Now, for the fixed headed pile, how this equation will change? Now, for fixed headed pile, because in this when we derive these equations, we assume that both the ends are free. So, these equations I can use only for the free headed pile, not for the fixed headed pile, because our assumptions are both the ends are free, but the fixed headed pile. So, your top or the head of the pile is fixed, but the bottom is free. So, that means the top head or the top of the pile or one end of the beam is fixed, another end is free, and for free headed pile both the ends are free. So, which is the condition by which these equations are developed. So, for free headed pile directly we can use these equations, but for the fixed headed pile we cannot. So, fixed headed pile, what to do? So, fixed headed pile, the solutions of the free headed pile equations or the equations for the free headed piles can be used if we apply a fixity for the fixed end. So, for example, suppose if we apply a horizontal force on a fixed headed pile. So, because of the fixity of the head, so a moment will generate on the head of the pile. So, and for the fixed headed pile, what is the end if one pile one end is fixed, what would be the slope? So, slope will be 0. So, that means this free headed pile equation we are want to use for the fixed headed pile, and how we will use that? So, that means we will use in such a way that first we assume that the pile is free headed. So, if I apply a h for the free headed pile, we will get a slope of this value for the free headed pile. Now, actually the slope at the fixed head will be 0 for fixed headed pile. So, that means this slope that will develop due to the free headed pile, that you have to make 0, and how that slope will be 0? Because when we apply a h or a fixed headed pile, so there will be a moment will generate. So, that moment is m 0 say. So, that moment will be generated, so that overall slope will be 0. So, that means what will be the thing? That means we apply a h for a free headed pile, we will get a slope. Now, due to the fixity for a fixed headed pile, there will be a moment m 0 will be generated, and that will act in the opposite side of the h, and because of m 0 in a free headed pile, if there will be a slope will be generated. So, that means the first initially we assume both the heads are free headed, both the piles under h and m condition are free headed piles. So, for h For free headed pile, there will be one slope, and for the moment applied in the free headed pile, there will be a slope theta. Now, this for the fixed, because of this fixed headed, now this both the slopes will be equal, then only the net slope will be 0. Okay. So, in such a way we have to calculate what will be the moment that will be induced due to the fixity of the pile. So, for example, here we assume that there will be only a horizontal, or here say only horizontal force is acting in the free headed. So, we will get the equations or the solutions for fine. For fixed head also there will be a horizontal force is acting. So, due to that horizontal force there will be a slope, and because of the fixity there will be a moment. So, because of that moment there will be another slope. So, we will equate that, because the net slope will be 0, and we will try to find what will be the value of m0 and what will be the fixed moment that will generated due to the fixity, so that net slope will be 0 at the head. Okay. So, under this concept we will use that slope for due to h is equal to how much? Minus 2 h lambda square. So, this is minus 2 h lambda square k h d, and k theta h at z equal to 0, because we are your fixed is here where z is equal to 0. Okay. So, now this is slope due to h. Now, slope due to m 0 is equal to 4 m 0 lambda square by k h d k theta m at z equal to 0. So, we will equate them, and we will not consider the sign, because these equations are given. What are the equations are given under this loading and moment direction? That means, loading is acting in this direction and moment is acting in the anti-clockwise direction. So, under these conditions these equations are given. So, if your direction of the load will change, this equation sign will also change. So, we have to use these equation under these loading directions, okay, loading or the moment or the forces direction. So, that means, here moment and the h is acting opposite direction, which is the actually the to make the net slope 0. So, we will take only the magnitude of the slopes. So, to make this slope 0, to make slope 0 at fixed end, we have to equate these two slope. That means, 2 h lambda square divided by k h d k theta h at z equal to 0, that will be equal to 4 m 0 lambda square divided by k h d k theta m at z equal to 0. So, finally, what are the moments are what is the moment we have to should be applied to make this slope 0. So, that moment is h divided by 2 lambda, this will be h divided by so this is lambda square, or just a minute. So, this is lambda square, this is lambda square, yeah. So, this will be 2 lambda square, and this is k theta h z equal to 0 divided by k theta m z equal to 0. That means, this k theta h and k theta m at z equal to 0 we have to determine. Okay. So, now this value we have to put in place of mg. So, that means, this moment will be developed due to the fixity of the pile head. Okay, so these are the equations. So, that we have developed for the pile, and then how we will calculate these coefficient, because this k rho h, k theta h, k m h, q h, rho m, theta m, m, q m. So, these are the values are given for different lambda L or z by L. So, different lambda L means 2, z by L, lambda L value. So, you have to calculate the lambda and the L, and then we multiply it if it is 2, and for different z. L is the length of the pile and z is at any depth. So, at any point you will get this coefficient, and if you put this coefficient in the values, then you will get the deflections here, moment, slope and bending moment, shear force. Now, this is for lambda L 2, this table is lambda L 3. So, these are the, this table is given. Then next is lambda L 4. So, similar table is given. So, this is the lambda L 4, then this is the lambda L 5. So, for different lambda L values, these tables are given, and then for different z by L we will get this coefficient, and once we get this coefficient we will get the required deflection, slope, bending moment and shear force at any depth of the pile. So, this class I have discussed that pile is treated as a finite beam. So, next class I will discuss if pile can be treated as a semi infinite beam, and then here I have discussed that kh is uniform throughout the depth or the length of the pile. So, next class I will discuss also that if kh varies linearly with depth of the pile. Thank you.